A Karnaugh map, often shortened to K-map, is a visual method used to simplify Boolean algebra expressions. By using this graphical technique, we can minimize the complexity of logic circuits, making them more efficient. It is a powerful tool for anyone working with digital logic and circuit design. Here is the structure of a two-variable K-map. In this K-map, there are two variables, a and b. Each variable has two possible values, 0 or 1, or in Boolean algebra we call them a prime b and b prime. The K-map consists of cells. Since we have two variables, the number of cells is 2 squared, which equals 4. Each cell corresponds to a minterm, m subscript 0, m subscript 1, m subscript 2, and m subscript 3. These minterms represent the product terms of the variables. For example, m subscript 0 corresponds to a prime b prime. The rows and columns are labeled with the values of the variables in such a way that adjacent cells differ by only one variable. This arrangement helps in simplifying the Boolean expression. Let's construct a two-variable K-map for the function f of a. B equals a prime b plus a b prime. This function consists of two minterms, m subscript 1 and m subscript 2. To construct the K-map, we place a 1 in the cells corresponding to these minterms. Specifically, we place a 1 in the cell where a is 0 and b is 1, which represents a prime b, and in the cell where a is 1 and b is 0, representing a b prime. The remaining cells are filled with zeros. Now let's simplify the two-variable K-map we constructed earlier. In this K-map, the ones are not adjacent to each other, so we cannot group them. Therefore, the simplified expression is the same as the original expression. F equals a prime b plus a b prime. This means that the function cannot be simplified further using a K-map. In this particular case, the K-map didn't help simplify the expression, but it's a fundamental concept to understand before moving on to more complex scenarios where K-maps can significantly reduce the complexity of Boolean functions. Let's examine the structure of a three-variable K-map. In this K-map, we have three variables, a, b, and c. Each variable can take on values of 0 or 1. The K-map consists of 2 cubed, which equals 8 cells. Each cell corresponds to a minterm, ranging from m subscript 0 to m subscript 7. The order of variables along the top and side follows gray code. The key feature is that adjacent cells differ by only 1 bit. This adjacency is what allows for simplification. Now let's construct a three-variable K-map for the function f of a, b, c, which equals the summation of minterms 1, 3, 5, and 7. To construct this K-map, we place a 1 in the cells corresponding to these minterms. Specifically, we place a 1 in the cells where the combination of a, b, and c values correspond to minterm 1, minterm 3, minterm 5, and minterm 7. The remaining cells are filled with zeros. This K-map visually represents the given Boolean function, making it easier to simplify. Here are the grouping rules for a three-variable K-map. First, group adjacent ones in powers of 2. This means you can group 2, 4, or 8 cells together but not 3 or 5. Make the groups as large as possible. Larger groups lead to simpler terms. Also, groups can wrap around the edges of the K-map. This is because the edge cells are also adjacent. These rules help you simplify the Boolean expression efficiently. Here is a group example. We can group 4 ones that will eliminate 2 variables. Also, we can group 2 ones. These are the basics of how grouping works in a K-map. Let's walk through an example of simplifying a three-variable K-map. In this example, we can group 4 cells vertically. The columns b prime c and bc are grouped together. This group of 4 cells simplifies to just c. The variable a is eliminated because it takes on both values, 0 and 1, within the group. So the simplified function f equals c. This demonstrates how K-maps can be used to simplify Boolean functions, leading to simpler and more efficient logic circuits. Here are some best practices to keep in mind when using K-maps. First, Use gray code ordering to ensure that adjacent cells differ by only one variable. Make the groups as large as possible. Cover all the ones exactly once and use the minimum number of groups necessary. Groups can overlap, which allows you to create larger groups and simplify the expression further. Also, consider wraparound edges as the edge cells are adjacent. The sizes of groups should be in powers of 2, such as 1, 2, 4, or 8. Check for prime implicants, which are the largest possible groups that cover at least one that is not covered by any other group. If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.